Hi, this is problem 10.2. In this problem, we are told we have a refrigerant 22 is the working fluid in a Carnot vapor refrigeration cycle for which the evaporator temperature is minus 30 degrees Celsius. Saturated vapor enters the condenser at 36 degrees Celsius and saturated liquid exit at the same temperature. The mass flow rate of refrigerant is 10 kg per minute. Determine A, the rate of heat transfer to the refrigerant passing through the evaporator in kilowatt. B, the net power input to the cycle in kilowatt. C, the coefficient of performance. D, the refrigeration capacity in tons. Now, regarding the Carnot vapor refrigeration cycle, and what does it mean? A Carnot vapor refrigeration cycle is a theoretical thermodynamic cycle that describes the most efficient way to create temperature difference in a refrigeration system. This cycle is utilized as a model or reference for a refrigeration cycle that runs between a constant temperature heat source and sink. And this process or this cycle is completely reversible. Reversible process means it can run in the opposite direction without leaving trace, no heat gain or loss from and to the environment or surrounding. And to have the highest efficiency, it means all processes are reversible. And again, the Carnot vapor refrigeration cycle is used as a reference by which real-world cycles are judged. So first thing, let's write down what is given to us. First thing, we are told that the working fluid is refrigerant 22R22. So we can refer to the properties for refrigerant R22 to solve this problem. And again, we're told that we are dealing with a Carnot vapor refrigeration cycle, which is a theoretical cycle. And the evaporator temperature, the refrigerant R22, that is operating inside the heat exchanger, which is the evaporator, its temperature is minus 30 degrees Celsius. And here we have a saturated vapor that will enter the condenser as a saturated vapor at a temperature of 36 degrees Celsius. And the refrigerant will exit the condenser as a saturated liquid at a temperature of 36 degrees Celsius. And the mass flow rate, which is mass per unit time, is 10 kg per minute. Next, we will write down what do we need to find. So in A, we are asked to find the rate of heat transfer. And the rate of heat transfer is the rate between the air that you want to cool and the refrigerant, because the air that you're cooling is hot, and the refrigerant that is entering the evaporator, the heat exchanger, at a temperature of minus 30 degrees Celsius. So there will be a heat transfer from the hot to the cold, and that's why the refrigerants evaporate. So we want to know this heat transfer, or kilojoule per unit time, or kilowatt. In B, we are asked to find the net power input. So we will have a net power input from the capacitor and an output power from the turbine. And we will see what do we mean by that. C, we are asked to find the coefficient of performance. Again, we want to find the maximum theoretical coefficient of performance that a cycle can operate. And refrigerant capacity, which is the same as A, but instead of finding it in kilowatts, we need to find it in tons. And here, what we would like to do is we would like to draw a schematic. A schematic is a simplified drawing or diagram that uses lines and symbols to convey important information, and it helps us visualize what is given and what do we need to find. So here we will have two things. The first one in here, we have this figure that represents the Carnot vapor refrigeration cycle. And here we will have the the graph, the temperature in degrees Celsius and the entropy in the horizontal, which is kilojoule per kilogram degree Kelvin. And this right here represent the processes for the Carnot vapor refrigeration cycle, where you're going to have two isothermal isobaric process, which will be from 4 to 1 and from 2 to 3, and we're going to have adiabatic processes, compress adiabatically from 1 to 2 and expand adiabatically from 3 to 4. And the main thing that this cycle will produce is this heat transfer between air from the conditioned space, like your room, to the refrigerant, the working fluid R22. So the exit air is a cold air, so it can cool the space that you are at. Now, the temperature and pressure of the refrigerant remain constant during the process from state 4 and state 1. The working fluid at state 4 enters as a two-phase liquid vapor mixture at a low pressure and low temperature, and leaves at low pressure, low temperature. And again, the process from state 4 to state 1 is isothermal process, isobaric process. Next, from state 1 to state 2, the refrigerant is compressed adiabatically from state 1, where it is a two-phase liquid vapor mixture, to state 2 adiabatically, mean without loss or heat, without loss or gain of heat from or to the surrounding. And the vapor, the refrigerant R22 will exit the compressor as a high temperature, high pressure, saturated vapor, and that's what we have in here. 2 is a saturated vapor. Then it will enter the condenser. The refrigerant passing passes from the condenser into from the compressor into the condenser, where it changes phase from saturated vapor to saturated liquid as a result of heat transfer. So here will be heat rejection. And the refrigerant will exit the condenser as a high temperature, high pressure, saturated liquid. And that's what we have in here in number 3. The refrigerant returns to the state at the inlet of the evaporator by expanding adiabatically through a turbine. So expanding adiabatically through a turbine from state 4 to from state 3 to state 4, returning back to the evaporator as a low temperature, low pressure. So here, what do we need to find? So first thing, we are told in the problem statement that the refrigerant, the working fluid, operates in the evaporator at minus 30 degrees Celsius. And the refrigerant operates in the condenser at 36 degrees Celsius. And we are told to find the Qn or Q evaporator. So how did we get this equation? When you do the mass and energy rate balance for a control volume, it will reduce to this equation, but that's another topic. And for the net power, we have the compressor. As you can see in here, we have input power. So we will use the same equation, the mass flow rate times the difference in specific heat, the high specific heat minus the low specific heat. And we have the work produced by the turbine, where you have the mass flow rate times the difference in specific enthalpy. Sorry, I meant specific enthalpy, from the high specific enthalpy minus the low specific enthalpy. And finally, we are asked to find the maximum theoretical coefficient of performance of any refrigeration cycle operating between regions at temperature cold and temperature hot. So here we're going to solve for A. Again, A, we are asked to find the rate of heat transfer, and the equation is the mass flow rate times the difference in specific enthalpies, H1 minus H4. Now, in here we have the mass flow rate, but we need to find the specific enthalpies. So let's take a look at the temperature entropy diagram in here. So what do we know? We know that at state 2, it's at a saturation vapor curve line, and the state 3 is at a saturated liquid line. So we can use the properties for refrigerant R22 at 36 degrees Celsius to find entropy, enthalpy, and other properties. So in here, we see that the entropy at state 1 is the same as the entropy at state 2, and the entropy at state 2 is at a saturation gas line or vapor line. And the same thing, the entropy at state 4 is the same as the entropy at state 3 at a saturation fluid line or liquid line operating at a 36 degrees Celsius, and from the table we can get the value. So we go to the properties of saturated refrigerant 22 liquid vapor, and we look for the temperature table, and it's located at page 901, and we go to a temperature, the rho, for 36 degrees Celsius, and from the table we can get the entropy values. And remember, S1 equal S2 equal to S sub G, and S sub G in here from the table is 0.8790, and the unit is kilojoule per kilogram degree Kelvin. And the same thing we're going to do for entropy at 4 equal entropy at 3, and the entropy at 3 is at saturation liquid, and we get this value. And also we can, from this table, we can get our saturated liquid. As you can see, H sub 2 is at a saturated vapor, it's H sub G, and H sub G is 260.11. And the same thing we're going to do for state 3, the specific enthalpy for state 3, which is 89.29. So here what we're going to do is we're going to use the equality equation, and that's I think in chapter 3 in the Thermodynamics book. So as you can see, at state 4 and state 1, it's inside the liquid vapor mixture region, inside this dome. So we're going to use this equation because at minus 30 degrees Celsius we can get H sub F from the temperature table, and the H and the evaporation H F sub G also from the table. But we need to find the quality, and we're going to use the same equation also to find the specific enthalpy at 4. So what do we need to do? So let's go back to what we know in here. So we know that the entropy at 1 is the same as the entropy at 2, and we have its value. So we're going to use the quality equation and apply it for the entropy. So it will be S sub F plus X S F sub G. And remember, this thing that the values that we want to get it for the specific entropy is at minus 30 degrees Celsius. So we will go to the table of minus 30 degrees Celsius, and we will extract the entropy values for S sub F and SF sub G. And remember, SF sub G is the difference between SG and SF. Then we're going to plug in the values, and that will be a simple algebraic equation, and you can solve for X. And we will do the same thing for S sub 4, which is equal to S sub 3 equal to S sub F, and we were able to find this value for S sub 3 from the 36 degrees Celsius row. And since we want to find the quality at 4, so we will refer to the minus 30 degrees Celsius column, and we will plug in the values that we extracted from the table. And again, we will do a simple algebra to find the 2x values, and these values will tell us at state 4 how much vapor is in the mixture, and in 1 also it will tell us how much vapor in that state. After we find these 2x values, we will plug it in back in here, and again we are referring to H sub 1 and H sub 2 here is operating at minus 30 degrees Celsius, so we will use the specific enthalpy for the minus 30 degrees Celsius. And that will give us 213.53, and it will give us 79.2 for H sub 4. Now going back to the original equation, we are given a 10 kilogram per minute. We will convert it to kilogram per second, so we can get kilowatt. I remember that 10 kilogram per minute times 1 minute is divided by 60 seconds. So that's why it's 10 by 60. And the difference between the enthalpy, and it will give us that the rate of heat transfer going into the evaporator is 22.4 kilowatt. Next, we will solve for B. Now, these are the values that we found from the tables and the values that we solved for in here. And now what we want to do is we want to find the net work. And remember, from the diagram, we had the capacitor working from 1 to 2, and the difference, and so it will be the mass flow rate times the high enthalpy minus the low enthalpy. And also the same thing for the turbine. Well, it will produce work, and from the high enthalpy to low enthalpy. And then we will plug in the values that we found from the tables and that we calculated in here. And it will give us that the net work power is 7.76 kilowatt. Next, we will also find the maximum theoretical coefficient of performance. And remember in here to convert your degree Celsius to degree Kelvin, and it will give you a coefficient of performance 3.7. And here we will do the final thing, which is D, to find the refrigerant capacity in tons. So what we will do is we will take the QN or the Q evaporator that we found, 22.4 kilowatt, and we will use this conversion factor. 1 ton is equivalent to 3.516 kilowatt, or 1 ton is equivalent to 3,516 watt. So the kilowatt will cancel with a kilowatt. It will give us that the rate of heat transfer, or the refrigerant capacity, is 6.4 ton. Thank you very much. Have a good day.